Hey, we've got Nicholas on board. Wonder if we got anybody else. Oh yeah, we got a good crowd. Look, Nicholas, Alex, Daniel, Julian. Bryce, Brian, Tyler, Reagan. I think there's others. I missed somebody. Daniel, Braxton. Yeah, we got a great crowd. And it's time. I'm actually a couple of minutes late. And we're in Thermo now. Did anybody have a question before we start our exciting lecture for today? Well, I guess nobody has a question, huh? Now let's see, this says mute all, but you guys can unmute anytime you want to talk to me. And there's Nathan and Bryce, good deal. Now what's our topic for today? Well, I don't know. Let me read this. It says enthalpy and specific heat. Well, we could talk about those. That'd be good. Yeah, those are wonderful topics. And you can still ask me a question. Otherwise, I'm going to launch into the exciting world of enthalpy and specific heat. But I want to do some problems too. I wrote down some problems. Here's some. All right, nobody said anything. I got to make sure that we're connecting. Hey, Bryce, say hello. Unmute and say hello. Bryce, we got a problem. I see your mouth moving, but I don't hear anything. Unmute.
Can you hear me now?
There you go. I heard something.
Okay, I'm using my phone to call in.
Oh, well, that's okay. Nathan, unmute and say hello. I want to make sure we're connected.
Hello.
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 Yeah, right. I think we're okay. All right, well, let's talk about enthalpy then. Now, it's in your book. Help me find it here. Let's see. You know what page it's on? Chapter 3, I think. Yeah, it's on page 86 in your book. And the topic right now is enthalpy. And you need to know something. That's not how the sophisticated people pronounce it, okay? They pronounce it enthalpy. So if you go to Caltech or Harvard, they're going to call it enthalpy, and so you'll know what they're talking about. But hey, I'm an Oklahoma guy, all right? And this is my class, and I can call it enthalpy if I want to. And here's the definition of it. There it is. That's the definition. And you could read that in your book there someplace. Yeah, I see it. It's on page 86. Only we're really more interested in the little letters. Let me get that picture out of there. There we go. We're interested in these little letters. Now, there is no little p. There's a big P, but there is a little v. See it? And that's the one that's more useful to us, the specific enthalpy, the specific internal energy, and the specific volume. Of course, that's pressure. Well, they have that equation too on page 87. This is on page 87. Okay. So what? What good is it? Well, let me show you what good it is. Let's see if I can show you what good it is. Now, if you took, we're going to do a little calculus here. If you wanted to get the change in enthalpy, it amounts to using calculus. So you go P delta V plus delta P V. You know what I did there? I used the product rule. That's the product rule, isn't it? I didn't lose you, did I? Hope not. Now, where enthalpy is valuable to us is when you have an isobaric process. There are some very important isobaric processes. For example, evaporation and evaporation, you guys like that because that cools off your car. Going down here in the summertime, driving your car, you turn on your air conditioner and cool air comes in there. It's because of your evaporator, and evaporation is a isobaric process. Now, if you have an isobaric process, this term here drops out, and what you have left is this. This term goes bye-bye because there is no change in pressure if you have an isobaric process. Now, we've seen an equation with delta U in it before, and it goes like this. And that equation has a name. It's a very important equation. Now, let me go to one of my wonderful students. Bryce, unmute and tell the crowd the name of this equation, Bryce. Go for it.
Is that the first law of thermodynamics?
Yeah, how about that? Yeah. It's the first law. Good going, Bryce. I was hoping I could trip you up on that, but I didn't get to trip Bryce up. He knows that's the first law. That's the first law for the little letters, you know, the specific internal energy. Now, some people call this the specific heat transfer. I prefer calling it the heat transfer per mass, but that's the same thing. And some people call this the specific work. I prefer calling it the work done per mass, but it's the same thing. Now, what I'm going to do is I'm going to make a substitution here. See that delta U? Look at, there's a delta U. I'm going to substitute it. Now, if you substitute that, you'll get this. See if you algebra students can make it to here with me. All I did was substitute that delta U in there. Yeah. Okay. So you're okay. Now, here's something interesting. If you got an isobar, it turns out that the work done is equal to P delta V. Let me see if I can show you that on a PV diagram. I need a little room here. Let me make some room here so I can show you. Yeah, we're going to make a PV diagram, and if you have an isobar, then it's flat. See, to go from 1 to 2, here's your P, here's your little v, and here's your state 2. And you know what? The area underneath the isobar is just a rectangle. And you know rectangles are base times the height. Well, the height is P, and the base is delta V. Going from here to here is just delta V. So the work done, the work per mass, the little w, is P delta V. So we could put that in here. Hey, you know what? If that's P delta V, and that's a negative, all of this stuff, it just goes bye-bye, doesn't it? And what do you have left? You have left the heat transfer per mass is the change in your enthalpy. Now, isn't that nice? That's why the enthalpy tables are so important. I had an air conditioner guy come out to my house, and he had a big, thick book on his front seat of his pickup truck, and it was all greasy because he got it all dirty, and I was just curious to look at it. And guess what it was? It was an enthalpy table. We have enthalpy tables in our book or in your electronic book. And why is enthalpy important? Because if you have an isobaric process, constant pressure process, the change in enthalpy gives you the heat transfer. If you want the big Q, that would be the change in the big H. Isn't that interesting? Now, I know what you students are going to do. You're going to get a hold of this equation like a dog gets that bone away from the dog. It's got that bone. It's not going to let go. And I know my students. They'll take this equation and they'll use it any old time, whether it's an isobar or not. But you'll get the wrong answer. The only time this equation works is if you have an isobar, okay? So be careful with it. Don't just use it all the time. Okay, now we've talked about enthalpy. Now the next topic is, do we have any comments or questions before we go into specific heat? We're going to talk about specific heat now. Nobody has anything to say about it? Okay, well, let's go on then. I need the room here. Say goodbye to all this wonderful stuff about enthalpy. But be careful of that equation I gave you. It only works for isobars. Now the next topic is called specific heat. Now they have specific heats for gases, for liquids, and for solids. And in fact, I think they have them in the back of your book. I bet they do. Let me go back here and see. Specific heat. I'm looking for specific heat. Solids, yeah, they got specific heat for solids. Then they have them for liquids. And they have them for gases. I'm on table A3, A4, and A5. A3 and A4. A3 is for solids, A4 is for liquids, and then for gases, it's table A5 in your electronic book or your paper book if you have one. The thing is, for gases, they have two different ones. Now here, they usually just have a single letter C, but in this particular book, they got a little P down there. They shouldn't. I think that's really a mistake. But for gases, you have a CP and a CV. There's two different ones for gases. And you'll see them in there. There's a CP and a CV. They're just all over the place. All right. Like for instance, for let's do aluminum. That would be this one here. For aluminum, if you want to find the change in internal energy of aluminum, you take your CP for the aluminum, which is 0.90. Tell you what, instead of doing aluminum, let's do water. No, we'll go ahead and do the aluminum. It's 0.90 kilojoules per kilogram Kelvin times your change in temperature, and that'll give you your change in your specific internal energy for aluminum. We'd have to have an example where you take a certain amount of aluminum and you heat it up, and as you make it hotter, you got more energy. Internal energy depends on temperature. Now water, let's do water, because I bet you already know this. Did you know for water, you'd have to look on this table here for liquids. And they have it there. They have liquid, yeah. There it is. There's water and water. There it is. For water, it's the way it works is that the specific heat of water is 1 calorie per gram per degree Celsius. I bet you've heard that. I bet you've heard that. It's 1 calorie per gram per degree Celsius. Now, if you want a kilocalorie, then you go 1 kilocalorie per kilogram per degree Celsius. That's the specific heat of liquid water, tiny bit with temperature. But I know you've heard of that before. Now, in the English system, water is 1 BTU per pound mass per degree Fahrenheit. In fact, that is a definition of what the BTU is. And this is the definition of what a calorie is, really. A calorie is the amount of energy to heat up 1 gram of water 1 degree Celsius. And you got to understand something. That's a little calorie. The calorie that they have on your candy bar, you buy a candy bar and it says so many calories, that's a capital C. See, this is a little c. There you go. It's a little c. A capital C is really a little calorie, really. Well, that's enough of that. Okay, that was fun, but what we really need is gases. That's what we'll be working with mostly. And here's the definition for gases. Let's see if I can find it in your book. This is chapter 3. And need a little room here. The actual definition for they have 2 of them. This is a definition. So we use 3 lines here. That tells you it's a definition. It's really a partial derivative. It's a partial derivative, and C sub P is a partial derivative and these specific heats are good for anything, refrigerants, any gases, that is. In the gaseous state, refrigerants, steam, neon, whatever. But in this class, you will only be using these for ideal gases. Now, if you have an ideal gas, you don't need a partial derivative. It turns out that you can use the ordinary derivative. They have a class called ordinary differential equations. I bet you've heard of it. Ordinary differential equations. They also have an advanced class called partial derivatives. I took a class called partial derivatives and Fourier analysis, but I was younger and better looking in those days, and that was well over 50 years ago. But I want to show you this. You don't need partials if you have an ideal gas, because your specific internal energy is a function of temperature alone, and your specific enthalpy is a function of temperature alone, so you don't need partials. See partials, that's when you have a function of more than one variable. But let me show you this. If you go to the, well, you guys have electronic books, but if you go in the back to where they have the ideal gases here, like air, for instance, they treat air at normal, our temperatures and pressures that we use in here, as an ideal gas. And let's say you want to look up the specific internal energy of air at, I don't know, 500 Kelvin. Well, I'm in this table back here. It's table A.7.1, and it says 359.84 kilojoules per kilogram. You notice I didn't have to put in anything else. All I needed was the temperature, because ideal gases are functions of temperature alone. You don't need anything else. And so you don't need a partial derivative. All you need is an ordinary derivative. So you get to use this equation here. Similarly, if you wanted the specific enthalpy of, say, air, there's a whole bunch of tables back here. You could look up carbon dioxide. Let's do that. So suppose you wanted the specific enthalpy for carbon dioxide. That's table A.8. Table A.8 at 500 degrees Kelvin. All right. I'm going to look it up. Here it says 401.52 kilojoules per kilogram. If you can find table A.8, that's the specific enthalpy at 500 Kelvin in the back of my book. Notice you didn't need anything else. All you need is carbon dioxide at that temperature and pressure behaves like an ideal gas. Now, do not be fooled about what it says up at the top, something about one bar of barometric pressure. This is good for all kinds of different pressures. They don't matter. The pressure doesn't matter. So therefore, you got this lovely equation here. Now, here's the bottom line. If you didn't understand anything up till now, you got to understand this. I'm going to do some algebra now. See if you can get to here with me. Can you make it from here to here? And here, see if you can make it. Can you make it from here to here? Can you make it? Well, if you can, we'll integrate this. And the bottom line is the change in specific internal energy is equal to this integral, C sub B dt. And the change in specific enthalpy is equal to this integral, C sub B dt. Now, if your C sub B is constant, you could pull it out. And you could just go C sub V delta T when you get through going from T1 to T2, or from 0 to T, whatever. And here, if the C sub P is constant, you can pull it out, and you'll have delta H equals C sub P delta T. Now be careful. If these change too much, and they do change with temperature, let me show you a graph so you can see what I'm talking about. They do, yeah, here we go. And let me make a picture of this so you can see what I'm talking about. On page 92 in your book, they have a graph. Actually, what they have is C sub P over R here, but you could make a similar graph of C sub P. And for all of the noble gases, C sub P is a constant. This is versus temperature. C sub P versus temperature. All the things like neon, helium, argon, and the other noble gases, they're constants. Now, air isn't exactly a constant. It kind of goes like this. It goes like this. But it sort of flattens out. And see, it's pretty dang flat out here over a wide temperature range. We're talking 1,000 degrees change in temperature out here. The C sub P just doesn't change hardly at all. And in that case, see, you could pull this out. It's a constant. And you can use that equation. Now, if you have a situation where the C sub P changes, then you have to go back and integrate. Or if you want delta U, you have to go back and integrate. Some of the things, like for instance, CO2 is notoriously bad. CO2 goes, kind of like that. CO2 the specific heat of CO2 changes. So unless your temperature interval is very small, I'm not sure you can pull that constant out. It's not constant. Going from here to here, for instance, that's not constant. The C sub P changes, see? And so you can't pull it out. And these are related, by the way. C sub P and C sub V are very much related. Let me see if I can show you that relationship. And that's probably enough theory. I think I've probably bored you pretty bad here. But I want to show you this relationship now between your specific heats and your gas constant. Okay, you all know the first law goes like this. Never mind, that's not what I want to do. We all know that the enthalpy is really, by definition, given by this. Okay. Now, if you have an ideal gas, then you can write it like this. Because PV is equal to RT, right? PV equals RT, yeah. Yeah, if you have an ideal gas, you can write that definition of enthalpy like that. Now watch this. We're going to do a little calculus now. R is just a constant. Can you get from here to here, calculus students? Now we just showed you something just a minute ago. Those of you that are still awake, we showed you can write this as C sub P delta T. That is, if you have a noble gas, or if you have some of the other gases that we were talking about, or the temperature range is not too big. If you can assume that the C sub P is constant, you can do that. And this is C sub V delta T. Now we're going to do a little algebra, see if you can follow this. Hey, we can get rid of the delta T's. And look at here, C sub P is equal to C sub V plus R. Or you could say R is equal to C sub P minus C sub V. Let's test this out and see if it works. Now we know what, for air, we know R is 0.287. Let's look up the C sub P for air. Go to the back, start snooping around, and find C sub P for air. Well, and there it is. I found it. It's table A.5. It's 1004. And C sub V, let's look that up. It is 0.717. Now get your calculators and subtract those, and let's see if that works. Okay, 0.287. Wait a minute. 1004 minus 0.717. Well, shazam. You know what? That worked pretty good. Look, there's a relationship between the gas constant and these things we've been calling specific heats. Let's do another one. Suppose you wanted to do, I don't know, carbon dioxide. Here we go. Carbon dioxide, the R is 0.1889. I'm getting these numbers from table A5. What's the C sub P for carbon dioxide? 0.842. And what is the C sub V for carbon dioxide? 0.653. Okay, let's subtract those and see what happens. 0.842 minus 0.653. Well, when I did that, when I subtracted those, I got 0.189. Somebody rounded off, well, we're okay. Well, that's all very well and good. Now there are several ways of finding these values, and maybe we can show you that here in a minute. But it's time. That's enough theory. I want to work some problems now. But did anybody have any comments or questions on our theory for today? You're awfully quiet. I hope you're still there. Hope I haven't lost anybody. Okay, well, let's work a problem. Here, let me erase all this stuff. I know you're taking good notes of this stuff. You've got good notes. Now this problem here, I thought we would do is 363. And I need to find it. Help me find it. 363. 363. Okay, a cylinder fitted with a frictionless piston contains 2 kilograms of refrigerant R134A vapor. Okay, it's going to have constant pressure. All right. Well, we really need the PV diagram, guys. Why don't we draw the device sketch here? Don't we have a system for doing this stuff? You draw the device sketch, and we have 2 kilograms of R134A. R134A. Hope you can read my writing. And it's going to be constant pressure. So we don't want to add any weights to it, but we're going to cool it off. I think we're going to have a heat transfer out. We're going to stick it in a bucket of ice water, okay? And so heat will be transferred out, and the piston will come down a little ways, like that. We're doing 363. And now we started with 2 kilograms. And we'll still have 2 kilograms. That hadn't gone anyplace. But this was at 350 kilopascals. And 100 Celsius. And now we're going to cool it so at constant pressure until it reaches a quality of 25%. You know what that means? I think that means you're going to have some liquid. There's going to be some liquid there in the bottom. You still have some vapor. I think this is all vapor, but we're going to find out. The way you find out is you draw a PV diagram. And you go back and look up R134A with me. And we need metric system R134A. Okay, I found it. Now what we want is 100 Celsius. Well, gee, where's 100 Celsius? Is dang near at the top of the dome. So our isotherm is going to go like this. There's 100 Celsius. And that pressure there is 4,064. I'm getting a sense of deja vu. Have we done this problem before? I don't remember.
Yeah, we did. We did it last class.
We did this problem before.
Yeah, we did
Good.
363, yeah.
Okay, well, I don't know if I want to do it again, but what I wanted to show you was they wanted to change the heat transfer. And see, we can get it. I don't think I showed you this before. We can get the heat transfer by going the delta H. That's what I was just telling you guys. So why don't we do that? That'd be fun. Even though we've done it before, that just means you're more familiar with it. And what we need is 350 kilopascals. Well, that's way the heck down here someplace. 350 kilo. Here we are. Here's state one. And state two is going to be in here. Yeah, I'm getting it. I knew we'd done this before. Here's state two. There's state one, there's state two. There's your isobar. And see, if you want the heat transfer per mass, all you got to do is go H2 minus H1. Well, H1, you can just look up in the table. Help me find it. It's 350. Oh, gee, now I remember we had to split the difference to get to 350, didn't we? And we had to go at 100 Celsius. And well, here we go. We're going to get it now. We're going to take to get to 350. You have to go. I'm getting H1 now in the tables. H1 is 490.48. You want halfway between that and 489. They didn't change much, did they? 0.52. And if you divide by 2, see, that was at 300 kilopascals, and that's at 400. If you want 350, you have to divide by 2. Okay, so here goes. Okay, I'm adding these up, and plus 489.52 divided by 2. Okay, we think H1, here's state 1, we think H1 is 490, right on the money. 490 kilojoules per kilogram. We did great. That's what we got the last time. I remember that. Now to get H2, what you do is you use this HF plus the quality. Now they said the quality, if you read the problem, didn't they say 25%? I don't know, I got lost. We're doing 363. Yep. Was that a yep? 25%? Yeah, I heard a yeah. Good going. So now what we got to do is at 350. Yeah, I remember this well. We were too lazy. It has a 350.9, and I was too lazy to interpolate. We just used 350. But we can get H2 pretty dang close. HF, if you look up for 350.9 actually, is 206.48 plus 0.25 and 174.38. Okay, we're going to get H2. Here goes. 206.48 plus 0.25 times 174.38. Comes out to be 250. Never mind the dot, dot, dot. Well, we got H1, we got H2. H2 is 490. H1 is 250. And when you subtract, I can't do that in my head. 490 minus 250, you should get 240 kilojoules per kilogram. Now, if they wanted big Q, and I think they do, and did I do that backwards?
just negative 240.
Well, I'm wondering, is it a negative 240? I think we did H1 right, and H2 is 250. I don't get a negative. I get a positive, don't you?
I think, yeah, it's negative 240 for Q. Is that right?
Well, Q is equal to the mass times little q.
Yeah, it looks like up there you may have subtracted H2 from H1.
Well, H2 is 2. Oh. Thank you so much. There's several of you that spoke up, and I appreciate it. I think we need 250 minus 490. I think that's better. I had them backwards, 490. So you get a negative 240. But now the mass is 2 kilograms, so you have to multiply by 2. I can do that. I'm getting a negative 480 kilojoules. That should be the answer, negative 480. This is 363. Let's see what the answer book says. Okay, I've got an answer book here, and it says Three's 363, right? I think I've got that here. Okay, 363. They have an answer, and the answer book in the back of my answer book, they're getting a Q of negative 469.2 kilojoules. Now, what do we get? We got negative 480. I wonder why there's a slight difference here.
When you were calculating H2, you put 174.38 instead of 194.38, I think.
Say that again, please.
When you're calculating H2, your 174 should be 194.
Oh, really? Okay, hang on a minute. Let me look that up. We're trying to find the 350. Yeah, there's 350. Really appreciate your help. Yeah, I'm using the wrong one. Dang it. I think I was using U's there. I don't want to use a stinking U's. Here's what I want. These are wrong. You know what those are? Those are U's. I screwed up. It's 206.75. Like my excellent student just helped me put another thank you point up here. It's 194.57. You have to multiply that. And so I'm a little bit off, and the reason why is I was putting in the U's. We don't want the U's, we want the H's. Okay, well, now let me get this, just a minute. 206.75 plus 0.25 times 194.57. It's 255. It's not 250, it's 255.4. So what we need, I think the 490 is okay, but what we need is 255.4. And then when you subtract the 490, here's what you get. You get minus 235. Minus 235. Now, what did the answer book say? But you see, you have to, that's little q. Little q is negative 235. If you want big Q, you got to multiply by 2. And you'll get negative 470. What did the answer book get? The answer book got negative 469.2, and we got negative 470. I think we did pretty good, especially when I used the right numbers out of the table. So we had an example of finding the heat. See, the heat transfer, that's what you're paying money for. You bought that car with the air conditioner and you want to keep cool. That costs you money. Or you either have to buy more gas to run it, or for your house, you have to pay electric bill. Okay, well, that was fun. Let's do another one now. Gee, I hope I haven't done this one. Was there any last comments or questions on that one? Okay, well, let's do another one. Here we go. We did pretty good on that one. And you know the method. You do a device sketch, and you do a PV diagram. And we learned a new trick today in that the heat transfer, be careful though, it only works for isobars. Now this one is 3176E. Now if we've done this together, somebody tell me and speak up. Otherwise I'll just bore you out of your gourds here. Let's see, 3176E. But that didn't hurt us any. Okay, 3176E. Piston, cylinder fitted with a frictionless piston. 4 pounds of superheated refrigerant R134A. Okay. The cylinder is now cool. Oh, constant pressure. You see that? It reaches a quality of 25%. Calculate the heat transfer. Okay. You know what? I think this is the same doggone problem or type of problem that we just did. Here, let's draw the device sketch. Here we go. It's a constant pressure. And I bet we start off, yeah, superheated. Yeah. We start off just vapor in here, see? And we cool it off. We have a heat transfer out. Stick it in a bucket of really freezing material there. And what will happen is the pressure will go down. No. The pressure stays the same, but the temperature will go down. And you'll condense. You'll get some liquid. This is R 170. It's R 134A. And you'll have some vapor, and it's going to be 25. It sounds like deja vu here. The quality is 0.25, but see, you have some liquid there in the bottom. You got some droplets that come dripping down the sides of your cylinder and collect in the bottom there, but the pressure stays the same. It starts off at 400 psi, and it ends up at 400 psi. But you know, I think the temperature changes. You've got 4 pounds mass, and it's at 200 Fahrenheit, 400 psi. Okay, we're going to find the heat transfer. Well, help me go back to the back and find R134A with me. Here we go. R134A. Oh, we want English, senor. Help me find English. R134A. Okay, I found it. Now, what did they say the temperature was to start with? I got lost. It's 200 Fahrenheit. No. Yeah, it starts off at 200 Fahrenheit. This starts off at 200 Fahrenheit, but it's going to get colder. I think. Okay. I think temperature is going to get colder. Well, let's draw the PV diagram so we can see what's going on here. Now we know we have 200 Fahrenheit. So, gee, it's way up towards the top again. I think it's the same idea as the last one. We're way up here at the top. This is 200 degrees Fahrenheit. And see, this pressure right here is 503 point something, 503.64 PSI. We're at 200 Fahrenheit. But wait a minute, we're at 400 PSI. You know what? 400 is smaller than 503. 400 PSI. Oh, we're out here. Here's state one. Okay. We'll go to your table and help me find 503.64. Well, they don't have a 503.64. I'll tell you what, they have a 500. No. We don't want that. We want 400. Yeah, they do have a 400. And they do have a 200 Fahrenheit. Hey, here we go. H1 is equal to 192.92. This is table F. Dot 10.2. That's H1. And I think we're going to go isobar. We're going to follow an isobar to state 2, just like we did before, except it's English. And at state 2, what do we want? We want 400 PSI. Okay. All right. Well, they don't have a 400, but they have a 400.392. That's pretty dang close to 400. So what we're going to do is, and by the way, the temperature there is 180. So let me draw that. See, it cooled off. We were at 200, and now we condensed partially, and we are at 180. And to get H2, here we go. H2. We're going to go, whoops. Wrong table. We're going to go, this time I'm not going to put in the U's, I'm going to put in the H's. There they are. And we want 400. Yeah, there we go. Okay, it's going to be 140.62 plus 0.25 times 43.74. This will give us H2. But you really need to find that. That's on table F.10.1. I'm going to wait for a minute until I hear a couple of students say they found these numbers. Can you go to your table and find those numbers for me?
Found them.
Yay, there's one. I need another one.
Yeah, I found them.
Yay, good going. Okay, now we're going to get H2, and then we'll be darn near done. You'll see. Here goes. 140.62 plus 0.25 times 43.74. I'm getting 151.56 BTUs per pound mass. Remember earlier today, I told you what a BTU is. Let me repeat that. What a BTU is the amount of heat transfer necessary to raise 1 pound mass of water 1 degree Fahrenheit. That's what a BTU is. Now you know. Okay, now let's find the heat transfer. Now here's the beauty of this. It's just equal H2 minus H1 because we have an isobar. Don't use this equation unless you have an isobar. But we have H2, it's sitting right here. And let me write that. 151, yeah. Minus H1, that's the 192.92. I got an answer of minus 41.4 BTUs per pound mass. But do they want the big Q? Let's see. 3176E. Yeah. See, what they want is the heat transfer, the big Q. That's equal to mass times the little q. Well, what's the mass? Did they ever tell us? Yeah, it's 4 pounds mass, it says. So what we're going to do is we're going to take 4 and we're going to multiply by the 41. Here goes. And I'm getting 165.5 BTUs. Yay, we think we have the answer. Now let me look and see what the answer book says. This was 3176E. I wonder if I have that. I hope I do, but I'm not sure. 3176. Okay, I'm trying to find it here. Okay. Boy, Jove, I have it here. Now here's what they say. The answer book says negative 165.5. Well, look at us. We got exactly what they got, so I feel pretty good about that. So we did that. Now, what's next? Did you have any comments or questions on that? Well, we have 12 minutes left. I want to show you the different ways of calculating some of these things. But I'm gonna have to erase all this. Are you happy? Any last words? Because I'm gonna erase all this. All right. Basically, we did the same problem in metric and in English, but that was good for us. We got to learn how to work in metric and English. Now, if you want to find, say, the change in enthalpy, we've told you why I think it's important. There are really 4 ways. One way, you can just go this here, and we gave you this equation. Here, let's do an example, shall we? Suppose you had Suppose you had air, maybe. Do we want to do air? Yeah, I think that'd be all right. Yeah. I might want to do something more exotic. Just a minute. Let me think about this. We could do air. Yeah, that'd be all right. Yeah, we're going to do air. Let's say we go from 1000 K to 2000 K. Gosh, that's an awfully, that's a way bit too much. We're getting close to the temperature of the sun there. Well, how about 1000 K to 1500 K? There we go. Now we're going to do the change in specific enthalpy for air. I've got 10 minutes, and I think we got enough time to do it in. Now, one way is just to use this formula. Now we're going to look up air. Now I happen to know it by heart. It's 1004 kilojoules per kilogram Kelvin, and you'd multiply by 500. So do that. And I'm going to go to my wonderful student that's stayed awake this whole time. Braxton, unmute and tell me what you get for the change in specific enthalpy.
502.
That's what I got. 502 kilojoules per kilogram. Now, there's another way to do this. There's actually 4 ways. This will be fun. The other way is, well, it's really like this. Remember, I told you, this is really what you get from the definition. You're treating air as an ideal gas. And see, here you don't have to pull it out because it will change. Air will change. The C sub P is not exactly constant. But here's the beautiful thing. They've already integrated this. And they have integral tables for air. If you'll go to the back, this is appendix table A.7.1. Look at A.7.1 with me and help me find air at 1500. And boy, Juve, I'm getting 1635.80. I need somebody to say, they can find that. Can you find that?
Yeah, I find it.
1500?
Yeah, I find it.
Yay, good going, proud of you. Now we're going to subtract. See, these are called ideal gas integral tables. That's the name of them. They have integrated. Isn't that lovely? They've done it for us. And at state 1, we're going to plop it down. It is, for air, it is 1046.22. Mohammed, can you find that one for 1000 Kelvin?
Yes, sir.
Yeah, he's got it. Okay, now we're going to subtract those. Here it goes. Take 1635.8 and subtract 1046.22. Now this answer is going to be a little better. Do you understand? For this answer, see, for this first answer, I got 502. For this answer here, I'm getting 589. Boy, that's rounded off to 6. there's a big difference. And the reason is this one has got an unhappy face, and this one is much happier. Much happier. Now, let me show you a third way. We have 7 minutes here. We have 7 minutes. Now, on this one here, we're going to take an average temperature. That's this method here. It's the average temperature method. The average temperature between 1,000 and 1,500, is that 12,500? Is it? No, is it 1,250? Is that halfway between 1,000 and 1,500? I think it is. That's the average, isn't it? Somebody say, uh-huh.
Uh-huh.
Yeah, that's the average temperature. And here's what we're going to do. We're going to use this equation here on table A.6. Table A.6. And delta H is equal to the integral what it is it's equal to, for air, it's equal to 105 minus 0.365 times theta. But see, the theta is the Kelvin temperature divided by 1,000 on this table A.6. So that would be 1.250. This probably doesn't make a lick of sense to you. Plus 0.85 times that theta, which is 1.250 squared, minus 0.39 times that theta cubed, 1.250 cubed. Okay, that should give you your delta H. Using the average specific heat at 1250. Plug all this stuff in. Now watch it. I'm not quite through yet. See what we're doing here is we're getting the average, and then we're going to multiply by delta T. So we're going to have to take all of this ugly stuff here and multiply it by 500. Oh gee, we only have 3 minutes left. But I want you to do that with me. Everybody do that. Put that in your calculators. Where did I get this 0.365? I got lost. Oh yeah, it's just in this table. Yeah, for air. Okay. Put all this in your table. 1.05 minus 0.365. 1.25 plus 0.85, 1.25 squared, minus 0.39, 1.25 cubed. All of this is equal to 1.160. And then see what we're going to do. That's kilojoules per kilogram Kelvin. We're going to multiply by the 500. And here's what you'll get. You get 580. Using this method, you get 580 kilojoules per kilogram. Now let's look and see. This third method, we get 580. kilojoules per kilogram. I have 2 minutes. I can outline method 4 for you. But can you see that this method is a whole lot better than the 502? 502 has an unhappy face on it because they were
Professor,
yeah.
I'm sorry to interrupt. On number 3, method number 3, where does it
Yeah.
say to multiply these terms by the average temperature? I don't see that in the equation. Is that the theta?
What we're getting, we're not multiplying by the average temperature. We're multiplying by the change in temperature times the average C sub P. See, I didn't explain this worth a darn to you guys, but all of this stuff right here, what that is C sub P. We're still using the same equation. It's just that that's the average C sub P.
Well, what I'm talking about is when you multiply like 0.85 times 1.250 and you square it.
In
Sorry,
the
I'm
equation,
getting
that's
right
the C1, C2, and C3.
Yeah,
In the chart, or in the graph, sorry.
yeah, this is C0, C sub 0, this is C1, this is C2, this is C3. This is one of those diminishing, what do they call that in math, where a series that, a vanishing series that you add up? Well, they have a,
I don't understand where the 1.250 is coming from and how that goes
Oh,
into the
okay.
equation.
look on table A6. A6. The 1.25, that came from, theta is your temperature, which is really, the average temperature is 1250. But you have to divide by 1,000. See up at the very top of that table, who am I talking to?
This is Nathan. I understand it now. If you need to move on, thank you, Theta. I get it now.
Oh, Nathan, it's too bad. It's so sad. I was going to show you the fourth method, but the fourth method is you actually integrate this stinking thing, and it would take me 20 minutes to integrate it, and we don't want to do that. But you should get an answer very close to this. This is probably the best of the 3 methods right here, but this is definitely better than 502. Well, it's sad, but our time together has come to an end. But there's different ways to find delta H. And see, delta U is just a function of delta H because they're related. Remember, H is equal to U plus PV. So if you can get delta H, you can get. Well, enjoy. You've got homework to do. Read your assignment, have fun. And I will see you, what, Tuesday? Right? Tuesday at 9:30?
Thank you.
Yeah, thank you, guys. It's been fun.
Yeah.
See you then.